So my main idea is to give the introduction to game theory and show some examples where it's being applied and how it is related to matrices. And the more importantly, how one can actually compute what you are really looking for. That's also very important. I have to tell you the story of my own way, how I entered into game theory. I joined the Indian Statistical Institute as a PhD student in 1962. And Professor C.R. Rao told me, first 3 years don't do anything, be studying. Okay. But anyway, I was previously in my MSc in statistics from Presidency College. I was interested in Wald's statistical decision functions. Abraham Wald, the famous statistician, tried to view the whole subject of statistics as a game between nature and statistician. Nature tries to hide the information, statistician wants to extract the information. Nature is not fully willing to reveal what its true state is. All it does is, it allows you to spy on itself. So think of this as the following. I don't know what is the average height of students in the campus. Okay? That average height is some unique number. So what you are allowed to do is, you are allowed to spy on a true number by collecting random observations. So I collect, say, 10 observations and I get the average height from those 10 observations, and think of this as my guess of the true value. You got me? The average height of the whole campus can be quite different from what I am getting from this particular sample. If I change a sample, I may get a different answer. So from sample to sample, it is going to be different. And so your issue is, what is the best way to estimate the true value? So that is the game which is being played. And Wald said, if theta is the true value, theta is the true value, the true average height. Theta hat is spied value based on a sample, on a random sample. Based on a random sample. So, nature said, he viewed, if you take theta hat minus theta square, that is the penalty which the statistician pays to nature. Think of nature as another person, statistician as a second person, nature as first person. The first person is hiding the information theta, the second person is trying to guess the theta value based on a sample, random sample, and once he guesses it as theta hat, this will vary from sample to sample. If some other person took another sample of size 10, it will be a different number. Each time it will be a different number. So this itself is what I call a random variable. Agree? So it's, when I take this thing and its expectation, its average, and that is what I call the This I call it as a risk function. This is called the risk function. So, if theta is the true value, theta hat is the procedure by which you get the estimate, and there is a risk involved, and that is measured by this number. So, one person wants to, the statistician wants to make it as small as possible. Nature wants to make it as large as possible by hiding the information theta. So, this is the approach which Abraham Wald took to reduce every statistical problem, every statistical procedure as purely a game. So he achieved significant progress and showed whatever is our intuitive solution which we get is the same as this solution, effectively. So this was something very inspiring for me, so I said I am going to work on statistical decision functions. So I took the book of Abraham Wald on statistical decision functions, and then the second chapter is called zero-sum two-person games. Okay, you have two players, and now he quit entire statistics. He concentrated mainly on the study of zero-sum two-person games. And when he came to that, myself and my colleague T. Parthasarathy, we were studying paper after paper, everything, and then I realized we couldn't fully grasp that level of mathematics. It had deep topological statements which with our background we couldn't follow. So we were struggling, and we were blessed with three outstanding probabilists. One was V.S. Varadarajan, another person was S.R.S. Varadhan, and the third person was K.R. Parthasarathy. Varadarajan had come just from US. He was itching to get good students to work in his area. And Varadhan was finishing his PhD thesis just at that time. As you know, Varadhan is perhaps the most outstanding living probabilist now. No one is anywhere close to Varadhan. And so he was just finishing his thesis, and he was going to teach everything, all basic mathematics like metric spaces, topology, analysis, everything. And Varadarajan was also teaching many of the subjects, especially on Hilbert space, etc. And that's how we got deeply into the right direction. But then there was a short paper which we could understand, and this paper is by one Kaplansky, Irving Kaplansky. It's called A Contribution to the Theory of Games. It's a just 5-page paper written purely based on matrix theory. Purely based on matrix theory. And even to this day, its appeal is phenomenal for us. It's remarkable, actually. It's a remarkable paper of 5 pages. And then we decided that I'm not going to work anymore in the statistics side. I'm going to work only on the game theory side. That's how I entered game theory. Okay? But the true inspiration was this paper work. I will come to it when I formally discuss the game theory part. And then, little later, only after finishing the PhD, in my PhD area at that time, Varadarajan was a very great inspiration in analysis. He was, and K.R. Parthasarathy was giving lectures on Markov chains, okay, in matrices. So we kind of appreciated that matrix theory is sitting at the center of many of them. And whatever you do in matrices, you extend it to the infinite dimension, you are at the functional analysis, nothing more. Okay? So the spirit of it is seen only in matrix theory. So it's, for a while, That was our initial inspiration. And slowly I also realized when we were studying papers after papers, we faced some special problems. And one of the problems is the following. I just give the example. Here is a balloon. And two guys are walking towards the balloon. Two guys are walking towards the balloon. The one, the closer a person goes to the balloon, he has greater accuracy. You follow me? See, when you go closer to the balloon, to hit the balloon, you have greater accuracy. Suppose each one has one pebble in his hand. So, there are two players. One has one pebble. Two also has one pebble. Two also has one pebble. So, with this pebble, you try to hit the balloon. So, when I go closer, my accuracy is higher. Agree? Then, so now the question is, the one who hits the balloon wins. Wins 1 rupee from the opponent. Okay? Now look at this problem in two ways. First is, what is the accuracy? You need to define what is the accuracy. So, a simple function can explain that accuracy. For example, if I travel a distance x and assume that this whole distance is 1 unit. 1 unit. If I travel a distance x, my accuracy is x. The probability of hitting this is x. If I travel half the distance, my accuracy to hit the balloon is half. If I travel 3/4 the distance, my accuracy is 3/4. If I travel the whole distance, I am sure to hit the balloon. Agreed? This is for me. For the opponent, this is for x, for player 1, y for player 2. Y for player 2. So now the thing is, suppose x is less than y. X is less than y. What does it mean? Player 1 wants to use the pebble slightly before player 2. Agreed? But they are not talking to each other. You remember? They are not talking to each other. I am only writing it as though a third person is watching it. Okay? So a third person has been informed by the two players. Player 1 says, I am going to hit at the point x. I will travel a distance x and hit. Player 2 says, I will travel a distance y and hit. Now the third person knows this, x is less than y. Neither one of the players know. Lack of information is very critical in all game theoretic analysis. Okay. Now, if he hits, he is going to win 1 rupee. Agree? So the chance he hits is x. With probability x, he makes 1 rupee. Okay? With probability 1 minus x, he will not hit. Agreed? With probability 1 minus x, he will not hit. Now, this pebble or the stone can be of two types. One visible, another invisible. Suppose it is a visible stone and you are watching the opponent and he lost it. Now you are player 2. You know already he has lost his pebble. Agreed? So what should you as player 2 do? Even though you plan to use the pebble at y, why should you? You could as well go closer and hit the balloon. Agreed? So, with probability 1 minus x, once this fellow fails, the other fellow is sure to hit the balloon by going closer to the thing. So with probability 1 minus x times 1, player 1 will lose 1 rupee. Agreed? So I can write this as, I can write it as a function kxy as 1 times x plus minus 1 times 1 minus x, which is 1 minus 2x minus 1 when x is less than y. This is only when x is less than y. It doesn't depend on, as long as x is less than y, for all such y's it's the same number. So similarly you can write down the expression for various things, and then if it is a visible thing, common sense says they both should shoot from the center at half the distance. You can, that's the best strategy for both players. So it's such a small thing it's a very simple problem, but it can go quite technical. Now if it is invisible, this function will be a more complex function. And then this was the thing which was interesting to me, and as a student. So I went through a famous paper of Schiffman, and I realized it is tied to the theory of positive operators. It led to the theory of positive operators. I didn't know the head or tail of that. So then I realized that there should be some, I talked to Professor Varadarajan. He said, why don't you study non-negative matrices? It seems related to that. That was his simple suggestion. And that's how I got into this non-negative matrices, the study of non-negative matrices. And it was triggered by this example. Very often, you really do not know, even if you are a PhD student, you don't know where your problem is going to be. It could come from any strange place. It's something which triggers you, something which tickles you. So you need to look for that tickling thing. Not by going through paper after paper, but when you go, suddenly you will find something very inspiring. And you go deep into it, you grind it, then you have all the skill to do it. You go around that topic and learn more and more. So that's what I used to do in ISI. And then there we had a good system. The students, the PhD students, they were imposed to give seminars. You have to give seminars. And one day Varadarajan simply said, I don't know what is a convex set, I said. And then he said, from next week onwards, you are giving a course of lectures on convex sets. There were no proper books also at that time. And then the other students, graduate students will sit and they will all they have the freedom to ask you, toss you, tear you to pieces. And that advantage is there when you are in a group of similar people. That was the thing which helped me. And that's how you add up, you realize that convex sets are related to game theory. You slowly realize these connections. It's a slow process, always. It's a slow process. And that's how I came also into non-negative matrices. And I realized many connections to all of them lead to deep theorems in functional analysis. Many deep theorems in functional analysis. I used to lecture for a whole year. Every week, one seminar, and then it will take a whole week to prepare for the next seminar as a student. So I knew exactly theorem 2.1 is what, 3.1 is what, like that. It used to be like that. But anyway, so those were the things which kind of led me to get properly into game theory, and then I started seeing them that those theorems can be proved by game theory. Many of those theorems of Krein and Rotman and all of them can be proved by game theory. I slowly recognized them. That was part of my thesis activity. Then I immediately went to England to give lectures as a lecturer at the University of Essex. There I was given the task of teaching linear programming. I have never learned linear programming before. I knew nothing. I knew how to, if I have given a problem, it was always grinding, but there was no formal way of solving a problem. I didn't know. So I struggled through by teaching the course. By teaching the course, I struggled through. So then I started respecting the computational side of this field. Almost all these fields, the computational side for a long time was neglected. Within even game theory, there are more theorems, there are more theories, but fewer computational tools for a long time. And while they were emerging, computer science also became a part of mathematics. It wasn't recognized fully as part of mathematics by regular mathematicians. They were not willing to even accept probability as part of mathematics, pure mathematicians. So that was the struggle which was going through. And finally, the computer science and its usefulness has wiped out, has told the people that here is something which is quite deep and useful, and you better learn this field. Okay? The same way, even game theory for a long time was considered purely as an esoteric mathematical kind of tool, and the economists who were supposed to use it didn't care much about it for a long time. But it all came into an important place when auctions were developed as how to develop good auctions. That led to understanding the so-called Nash equilibria in game theory. I'm going to talk about all of them formally, but I'm just telling. It was auction theory which triggered all economists to get into game theory. If you take any worthy economics department anywhere in US, you will have a sizable number of game theorists sitting there. They may be doing game theory but may put it in the language of economics. The whole microeconomic theory is written in the language of game theory. And then the same way the biologists, what is called evolutionary biology. And that's also another place where game theory enters. And the third one is what is called ethical way of dividing and cooperation. And that is another area which also is an important area. Now let me start with a few slides. Okay. So for example, in a business school where I taught something, what modern business is not just outsmarting competition, market share, fighting back, beating opponents, locking customers. All these things are not good strategies. Listen to customers, work with suppliers. With a lack of cooperation, you can lose all you made for. So you need cooperation is also an important aspect of playing games. See, what is a game? Game means a bunch of people, they follow certain rules and then they are acting according to the rules. It's a business, one such. So you're dealing with customers as well as suppliers, etc. For example, US Airlines lost all the profits made until 1990 during this period in a tough price war. So when you go on a price war, one can lose. Okay. You succeed only when others also succeed, is the theme. Our scriptures say, Sarve janaste sukhino bhavantu. Samasta san mangalani santu. In other words, let all people live in happiness, let there be peace all around. Okay. So what is business then? For example, why am I talking about all these things? It's also tied to the game theory. That's the reason. It's just like running a good family. Parents and children cooperate to create the best pie. They fight and compete to share the fruits of cooperation. In a sense, modern game theory can as well be dubbed co-opetition. That means there is a cooperation and competition. Okay. Players in business are both Mr. Jekyll and Mr. Hyde. There is a Tamil song, Konjam Nilavu, Konjam Niruppu, Konjam Mirugam, Konjam Kadavul. That means sometimes she is cool as a moon, sometimes ferocious as fire. Sometimes she is an animal, at other times she is an angel. Okay? So that's the kind of thing. Okay. Where is game theory applied? Winning elections, resolving legal disputes, apportioning environmental costs, measuring the importance of factors that contribute to the spread of diseases, choosing one's mates. The most recent work of my PhD student is on studying choosing mates. Okay? And maybe I could choose that one first to give an idea. Okay? How something can be very recent, it's tied to the matrix theory, and at the same time it is quite difficult. Let me start with that one, because I am only trying to motivate where game theory is found. Okay? Suppose there are, say, 5 girls. Call them as G1, G2, G3, G4, G5. There are 5 boys, B1, B2, B3, B4, B5. I'm going to fill up this with a matrix of only zeros and ones. Okay? If I put a 1, which means the girl 1 likes boy 1 and boy 1 also likes girl 1. Assume they are all of the marriageable age. Assume they are all of the marriageable age. G1, B1, if I put 1, which means the girl 1 and boy 1, they like each other. If I put 0, this means sometimes both of them don't like each other. Sometimes it may be a one-way traffic. Okay? The boy may like the girl, but the girl may not care for the boy. So in which case I put a 0. Agreed? So I fill up this whole thing with 0, 1, 1, 0, 1, 1, 1. Okay. I have filled up this with a 0, 1 matrix. Okay? Now, what is the maximum number of marriages that can take place? 5? So, can you suggest one such? Along the diagonal, G1 likes B1, G2 likes B2, G5 likes B5. Okay? So this part is clear. So the coalitional, what I call as, for the society, the maximum number of marriages possible is 5. Agreed? Because there are only 5 people and they are able to also find correct mates. Okay. Now, the next step is the critical step. G1 and B1 are married. Let me make it this way, for example. Suppose, change it to this, okay? G1 and B1 are married, G2 and B2 are married, etc. Now, G1 and B1 as a family, I want to measure who is the dominant person. Is G1 the dominant person or B1 the dominant person? Huh? B1 or G1? B1. Why B1 is a dominant person? He has more choices. Okay, he has more choices. Whereas G1, if she doesn't get married to this guy, she has to remain a spinster for the rest of her life. That's the situation. So, G1 and B1, when you say, G1 is the dominant person. Its dominant is just ranking now. Agreed? But I want to measure exactly, suppose their whole power is 1 unit. What is the relative power of B1 and what is the relative power of G1 in this? One has to have some measure. How to measure that is also part of game theory. Okay? And my most recent PhD student, John Hadwick, his thesis was on a very efficient algorithm to measure the relative power of the married couple. Who is stronger of the two? It doesn't necessarily mean this one is 3 and this one is 1. It is not like 1/3, 1/4, 3/4 like that. It's much more complex than that. How to do this one? Okay? And this is what is called study of cooperative game theory. It's called cooperative game theory. And in this sense, here I am writing it as purely matrix, etc. A more general situation is what is called the so-called marriage problem. Okay? And I can get into it, but it will be, I have to do it a little later. Right now I have to postpone it. In fact, it was a marriage problem which won Nobel Prize for Lloyd Shapley and Alvin Roth. Only in 2012 they won the Nobel Prize in economics for their work. It is a 3-page paper in American Mathematical Monthly. I can tell you that much. So the fundamental work is always, it takes a while to be recognized. Let me see what I have, the next one. What is it? Oh. Is it the one? Okay. Now I am starting with something quite formal. Okay? There are, when game theory was studied, it was studied with no secrecy. People are playing this game. What is the game? You have 4 baskets. Agreed? The first basket has 69 apples. The second one has 54 apples, 18 apples, 46 apples. Okay? There are 2 players. There are 2 players. Player 1 can choose any of these baskets and remove at least one. He has to remove at least one, and also even the entire thing. You can even empty the whole basket, but at least one you must remove. Then once player 1 has done it, then it is 2's turn. You follow me? 2 has to remove at least one or whatever he wants. But each time the choice is only from one basket. This game continues till all the baskets are empty. The one who is responsible for emptying the very last basket, all the other baskets were empty, there was one basket which had some. The one who was responsible for emptying the very last basket is the winner of the game. Follow me? The winner of the game. So, this was studied as a paper in the most prestigious journal of those in mathematics. Any mathematician will agree, Annals of Mathematics is the journal. In Annals of Mathematics, even before game theory was actually formally developed, this guy studied this game and gave a beautiful solution. I talk about this in all high schools. Sometimes when I meet high school talks, elementary school talks even, sometimes I talk about it. Why? I'm now going to give explicitly the solution, how to play this game. And the question is, who is the winner? The winner is one who, no matter what the opponent does, can always force the game to his side. Okay? The winner is one who, because he has no control over, after his first round, it is the other player's choice. He doesn't know what the other player is going to do, but still he must play intelligently to see that he always gets a chance to play one more round. You follow me? He always gets a chance to play one more round to play this game. Then he becomes the winner, if he can do that. Okay. Now, this one has a very beautiful application of representing numbers by binary form. Okay? So, let me write down binary representation. Okay. Now, can you note down the numbers? No. 69, 54, 18, 46. Okay? So now write them as binary numbers. So it is 64 plus 4 plus 1. Okay? This one is 32 plus 16, 48, 52 plus 2, 54. Okay? So on the top I have written 2 power 6 times 1, 2 power 5 times 0, etc., etc. So in the binary representation. So you fill up these numbers in binary form. Agree? Now, simply add the column total as though they are regular numbers. Okay? As though they are regular numbers. Add them. So here is a key theorem. If the column totals are all even, first player will lose. Will always lose. Will always lose against an intelligent second player. against an intelligent second player. Against an intelligent second player, the first player will lose if all the column totals are even. So what does this say? The column totals are not all even. So there is a good way of player 1 to win the game. Theorem 1 says, this next theorem says, in all other cases, player 1 can win playing intelligently. Also, it requires playing intelligently. What do you mean by playing intelligently? If suppose theorem 2, God came and told you this. God came and told you the theorem 2, believe me. He says, if all the column totals are even, there is no chance for player 1 to win. Okay? So, but if the column total somewhere it is odd, the second theorem says, in all other cases, player 1 can win playing intelligently. What do you mean by playing intelligently? That's what we have to appreciate. Playing intelligently means you choose and remove some from some basket such that the new numbers, when you write it down in binary form and take the totals, etc., now it is the chance for second player to play and you want him to lose. He will lose provided all the column totals are even. Are you with me? See, you have to appreciate the subtle point that if the column totals somewhere it is odd, you need to carefully select a basket and remove some, and what you leave next round consists of a situation where the new player is facing all column totals even. Then this theorem says he cannot win. Player 2 cannot win. Therefore, player 1 must win. So, one's aim must be always to somehow do this one. Do you follow me? Okay. So, how do I do that? The best thing is see, for example, if I remove 2 power 6 is 64, yes? Yes. So if I remove 64, this will become 0, therefore it is an even. Agreed? But unfortunately there is odd here. Odd here, odd here. So if I only remove 64, then the opponent is going to win if you made a wrong choice. So you need to choose in such a way that every one of these things is even. So what I can do is, I can remove this, so this becomes even. I can remove, you see, you have chosen from here. You can't choose different basket, you have to choose only this basket. So you removed this one, so this becomes 0. This remains 2. This remains 2. Unfortunately, you cannot remove from here because this is 0 here. This is 1. So, but you can add 1 here. You can add 1 because what you are adding is much less than what you are removing. So essentially you are removing. Do you follow me? So you can add 1 here, and here you can remove 1, so that this becomes, you can add 1 here, so that this is even. Do you follow me? It's a subtle point to appreciate. Okay. So what I am now going to do is, I am choosing the very first basket. Net effect, net removal equals 2 power 6 I am removing, and then I am less 2 power 3 because I am adding removing I am adding I am removing. Which is 64 minus 8 plus 4 minus 2 plus 1. 69, remove 59. Suppose I remove 59 from the first one. So now we are left with, let's write it down. Okay? I may write my calculation. Please pardon me. My father taught me only to memorize all in Tamil. He taught me all the multiplication tables and everything. Even in Chicago, I used to teach the statistics courses like regression or test of hypothesis or chi-square test, whatever it is. Chi-square normally involves a lot of squares and adding and everything. It's not mechanically, you do that one in your own language, and that's faster. Okay. So the first one is now left with 10. Now the second is 54, 18, 46. So we can write down. Okay? We can write down and check that. So then everything will be even. Now what is the first theorem say? What is the reason why it works? It works because of the following simple observation. 1 plus 2 plus 2 power n minus 1 equals 2 power n minus 1. Agreed? That means as long as you remove 2 power n, you can even add 1 to every one of the other places. Nothing is lost. Still it will be removing something. This is the crux for that argument also. So when you should try to play the game with somebody who doesn't know this. So you know the binary system and everything. You can play with anybody and try to defeat the person. Okay? Yeah.
Say you remove
yeah. I'm not following you.
You remove the entire basket from
Only so many of those fruits. You don't remove all the fruits. You remove so much and leave some. So that is still a non-empty basket. But the game ends only when all the baskets are empty. And the first person who achieved that, making it empty, is the winner. So this is a beautiful combinatorial game. Okay? The first beautiful combinatorial game. And this one precedes anything of game theory. And game theory started with John von Neumann. He proved in 1928 the so-called celebrated minimax theorem. He proved the so-called minimax theorem. That is the starting point of formal game theory. And there was a lot of fight as to the ownership of this theorem. In fact, there is a famous, you have heard of Borel sets, yes? The same Borel was interested in studying, in some sense, imagine any game is some matrix. Think of any game as a matrix. He was able to prove this theorem for matrices of size 3 by 3. But he couldn't prove for 4 by 4. He believed it is false, the theorem is false. And von Neumann, he was a 20-year-old boy who proved this theorem in a very long, incredibly difficult arguments, okay, of in small print, something like 20 pages of proof. And then, Borel being a French mathematician, the French people always have the pride that they are the discoverers of all mathematically deep works. So, people were pushing other mathematicians to write against von Neumann. Borel did something, this. And then von Neumann had to actually defend. He was not one such type. He said, I am fortunate to work in the area which Borel initiated. The only difference is Borel never believed in the theorem. I proved the theorem, the decisive theorem. Otherwise, there is no, the subject has no value. If there is no theorem, what is the subject there? Okay. Anyway, then this is one combinatorial game. I want to introduce one more combinatorial game. Okay? See, there are many combinatorial games of special kind, general games of, I will come to these things. Perfect information game, Zermelo's theorem, locate the winner, and the last one, game of X. I want to first talk about game of X. Okay? It's a combinatorial game. What is that? Let's look at this. Look at this board. Okay? As a rule, this is a boundary. The top, that's the boundary. You get the point? Somehow, you think of them as houses. Think of them as houses. All these houses on this left east boundary, all these houses, they are already pre-assigned to player 1. Okay? All these houses on the right boundary, except for this one, are again pre-assigned to player 1. The same way, all these houses on the top, except for this and that, are assigned to player 2. Here, the same way. Okay? Why should you do this kind? Don't question me, for the time being taken. It's mainly a mathematical construct. Okay? Every one of these vertex is a house. So each one of these vertex is a house. This is a house, this is a house. Okay? Now the players can alternate, or somebody can proxy anything. So these houses are either occupied by player 1 or by player 2. Okay? These other boundary houses are fixed. Only the interior houses are for grab. Now, I have a notion of adjacent houses. Okay? I have a notion of adjacent houses. So if this house, what is an adjacent house to this? Can you intuitively, which one is adjacent? This one is adjacent. How about this? How about this? How about this? So they are adjacent by our common sense. Now we have, I want to call this one and this one also adjacent to this. I want to call this one as well as this one adjacent. But I don't want to call this and this as adjacent to this. I want to call 45 degree, this one alone is adjacent, not the other one. Okay? And there should be some kind of a common sense reason for that. So let us give the coordinates. Say for example, this coordinate is 7, 19. The x coordinate is 7, y coordinate is 19. This will be 7. Huh? Yeah, 8, 19. How about this one? 6, 19. This one? 6, 18. This one? 7, 8, 18. And this one? 820. Now look at, with reference to this only I am studying what are its adjacent vertices. See, here both coordinates, 7, 19, 8, 19, the coordinates are less than or equal to the coordinates here. So between these, the coordinates of this less than or equal to, in both coordinates. Agreed? And the maximum difference is 1 unit. So the coordinates are ordered totally and the maximum difference is 1. These two conditions will say, for example, this one is 620, this is 719. So these two are not adjacent according to my definition. That means they can, in the first coordinate this one is smaller than this, in the second coordinate this one is larger. No. Then only I want to say they are adjacent. This is a very key observation. You follow me? Key observation. Now, the theorem says, it's called the game of X theorem. It says the following. No matter how you fill it up with 2's and 1's, whether they intentionally play with intelligence or they ask a monkey to throw 1 or 2 at one of these things, no matter what happens, there will be one person, the person who can start from his own boundary, one boundary to the other boundary, traveling only along adjacent path. Okay? So for example, let's do this, say 2, 2, 2, 2, 2, 2, okay? Then I go up 2, 2, 2, 2, 2, 2, 2, 2, 2, I am stuck. Okay? I don't know whether I can connect from here to here. Similarly, if I start from this side, I don't know where 1, 1, 1, I am stuck. The theorem says there is always one winner. There is no draw. Exactly one person must win. Okay? And the beautiful part is how to find a winning path of that player. Okay? How to find a winning path for that player is itself an interesting question. Okay. What I do is, it is this path actually. So is this path. There may be several winning paths also. I found one path. Okay, I found one path. And this is also closely tied to what is called linear complementarity and study of Nash equilibria. We will come to them also. It is tied to the same idea. Only thing which I can give, see, start at this corner. Okay, start at this corner. This one is already allocated to 1, this one is allocated to 2. The inside one can be for anybody. Suppose it was allocated to 2, as it is in this picture. So if you look at this triangle 1, 2, 2, there are, this triangle, the 3 vertices get only 2 labels. The 3 vertices get only 2 labels, 1 and 2. So here is one side with 1, 2. Here is another side with 1, 2. Okay? Here is another side with 1, 2. And this is the old 2, this is the new 2. This is the old 2 which was pre-assigned. This is the new 2 which you are coming to. Now what I do is, I want to remove this old 2. So what I do is the following. I'm just giving you the intuition. Okay. This is 1, this is 2, this is 2. So this is the old, this is the new. So what I do is, I remove this old 2 and keep this new 2 and form a triangle with 3 adjacent. These 3 vertices are adjacent. You can check this, this and this are adjacent vertices. Adjacent in my language. So if I remove this side and keep this one and form a new triangle, what will be the triangle? The only way you can form a triangle with this, this is the new triangle. It's called adjacent triangle. It's called adjacent triangle. And then what it will do is, these 2 are adjacent, these 2 are adjacent, these 2 are also adjacent. Agreed? It's an adjacent triangle. But now already its number is 1. Agreed? Because it is on the border. Already it has 1. So this is the new one. This is the old one. So I want to toss this old one and use only this new one and 2 and find an adjacent triangle common to this. This will be the triangle. So that is the kind of triangle formation which I am doing. Triangle formation. And it has to somehow reach either this side or this side. And when you notice it, on one face of it, it will all be 2's. On the other face of it, it will all be 1's kind. Whichever direction it hits, that wins. That's the idea of the proof. But it takes a little more effort to formalize it. Okay? So all it really says is, the game of X has always a winner. And even though it is a simple game, it is mathematically a very deep game. Mathematically a very deep game. Why? It also tells you how to find approximate fixed points. It's called how to compute approximate fixed points. Of maps, continuous maps from square to square. If you take a unit square and for each point you associate another point in the unit square and this map is continuous, then there is a point which goes to the same point under the map. It's called Brouwer's fixed point. And this game, playing this game tells you how to find the approximate fixed point. Now, basic idea is, it is a discretization of the original problem. Okay? I do know approximate fixed point is somewhere one of these points, say. If it is a very fine discretization, it is one of these points. So you have two choices. You can check from every one of these points to come to the answer. That is brutal enumeration. Agreed? But what this one says is, don't look for the solution everywhere. Look for the solution by building this path. By building this path. When you will not be able to, if you cannot build the path, then you have reached the answer. That's what it is. But it's a subtle point to be appreciated with certain amount of analysis. Okay? You need something to appreciate through uniform continuity, okay, and uniform convergence, etc. Anyway, that's not the point. The point is the discretization of this game is key to even approximate fixed point. They are formally programmed, etc. In economic models to find the competitive equilibrium prices, etc. This is the kind of thing which is used. Okay. Oh, yeah. Okay. I don't know. I can talk for hours and hours. That's it. Okay. Yes, yes. Please. I'm also happy to stop for a while. Yeah. But I want to go slow. Please also don't just listen to me. If you don't follow something, stop me. If you are asking, you are not only helping yourself, you are helping the other person who would like to ask, but who is hesitating. See, the more people understand each one, the better it is.
Yeah, workshop is meant for.
Yes, but the workshop is meant also for tearing me apart, questioning me, and I don't follow this. Yeah, that's the kind of thing which is needed. That's all I. So I can go slower than this, no problem. No problem. I can go slower than this. This is basically an introduction. I haven't still started the formal thing with matrices, everything. I will do that one slowly.
Now we will be using next session also for
continuation of this. There is no tutorial for today. Tomorrow I can give some homework and things like that, and where I sit and listen to you or do something. Okay.